Hydrogen bonds provide a strong attraction between water molecules. This attraction results in 5 key properties of water. The first property is that water molecules experience cohesion. Cohesion is the attraction between two of the same molecules. This attraction holds molecules of a substance together. In the case of water, adjacent water molecules are attracted to each other due to hydrogen bonding. Thus, hydrogen bonds result in cohesion. Cohesion is responsible for water's high surface tension. Surface tension is a measure of how much force is required to break the surface of a liquid. The higher the surface tension of a liquid, the more difficult it is to break the surface. Hydrogen bonds that link water molecules at the surface create a thin film that is difficult to break. This phenomena is observed when you place a small paperclip on water. Even though the paperclip has a higher density than water, it will stay afloat because the surface of the water stays intact. We will now move on to the second property of water. Water has a high specific heat. Specific heat is the amount of heat added to 1 gram of substance to raise the temperature by 1 degree Celsius. Because water has a high specific heat, a large amount of heat must be added to raise the temperature of water. Let's compare the specific heat of liquid water and solid iron. The specific heat of liquid water is 4.18 joules. In other words, it takes 4.18 joules to raise the temperature of 1 gram of liquid water by 1 degree Celsius. Joules is a unit of measure for heat energy. Another unit that is commonly used to measure heat energy is the calorie. 1 calorie is equal to 4.18 joules. This means that the specific heat of water is also equivalent to 1 calorie. Solid iron, on the other hand, has much lower specific heat of 0.45 joules. It only takes 0.45 joules to raise the temperature of 1 gram of solid iron by 1 degree Celsius. So what causes water to have such high specific heat? The answer is hydrogen bonds. When water is heated, most of the heat energy is used to break hydrogen bonds rather than increase water temperature. In summary, it takes much less heat energy to raise the temperature of solid iron than liquid water. This phenomenon can be observed when you heat water in an iron pot. After heating the pot briefly, you will notice that the pot becomes extremely hot and the water is only lukewarm. Even though the same amount of heat is added to the iron and water, the temperature of the iron increases more significantly because less heat energy is required to raise the temperature of iron. High specific heat of water is important to life. The ability to absorb a large amount of heat energy without much temperature change allows large bodies of water to moderate temperature. Here we have a picture of an ocean with 2 coastlines and an inland region. In hot environments, oceans can absorb a large amount of heat energy. In cold environments, stored heat energy in the ocean can be released. In this way, these large bodies of water prevent large temperature fluctuations. This is the reason why coastlines have a more mild temperature compared to inland areas. Let's talk about the third property of water. Water has a high heat of vaporization. The heat of vaporization is the amount of energy required to transition 1 gram of a substance in its liquid to gas phase. Water has a high heat of vaporization because in order to vaporize, the hydrogen bonds in the liquid phase must be broken first. Let's see how a high heat of vaporization is important to life. Suppose an athlete was exercising intensively. Here is a picture of her sweat-covered arm. Let's zoom in on her arm. Heat from her body is constantly being transmitted to the water molecules in her sweat. The transfer of heat out of the body cools the athlete. Eventually, enough heat energy is transferred to evaporate the water molecules. This process is known as evaporative cooling. Now let's move on to talk about the fourth property of water. Water is an extremely good solvent. Before we discuss why water is a good solvent, let's briefly go over some definitions. If we start adding sodium chloride to a beaker of distilled water, the sodium chloride dissolves. We have just prepared a solution of sodium chloride. There are two components of a solution. The solvent, in this case water, dissolves the solute, in this case sodium chloride. If we zoom in on the solution, you will observe that water interacts with the positively charged sodium and negatively charged chloride in a specific orientation. Recall that the polar water molecule is partially positive at the hydrogen and partially negative at the oxygen. For this reason, water will position itself so that the oxygen interacts with the sodium ion and the hydrogen interacts with the chloride ion. This interaction between opposing charges allows the water to dissolve the sodium chloride. Water dissolves any solute that is either polar or electrically charged. Given that there are so many polar and electrically charged substances in nature, water is capable of dissolving a wide variety of substances. This makes water a good solvent. The fifth property of water is that water is less dense in solid than liquid form. This property is observed when an ice cube placed in liquid water floats. This physical property is unique to water, as most substances are more dense as a solid and sink when placed in its liquid form. The density of water varies depending on temperature. Let's examine how temperature affects water density. At 4 degrees Celsius, water molecules are closest to each other. Thus, water is most dense at 4 degrees Celsius. As you heat water above 4 degrees Celsius, the water molecules are more spaced out. For this reason, the density of water decreases. This decrease in density upon heating is not unique to water and occurs in all substances. When the temperature drops below 4 degrees, the molecules become more spaced out and density decreases. The density decreases until the temperature is 0 degrees Celsius and water molecules are locked in position. This structure of interlocked water molecules is referred to as crystalline structure. Each water molecule is kept at a distance from each other. This spaced out arrangement of water decreases its density. The formation of the crystalline structure is made possible by hydrogen bonding. This ends our discussion about the 5 properties of water. Let's talk about a common phenomenon that occurs in water. Here we have a zoomed-in picture of 2 water molecules that are connected by a hydrogen bond. At times, there is a transfer of a proton of a hydrogen atom from one water molecule to the other. Because one of the water molecules loses a proton and the other gains a proton, two ions form: a negatively charged hydroxide, OH-, and a positively charged hydronium, H3O+. The hydronium ion can also be written as H+. Scientists came up with a convenient scale to measure the relative concentration of hydronium and hydroxide. This scale is known as the pH scale and ranges from 0 to 14. Neutral solutions have a pH of 7. The concentrations of hydronium and hydroxide are equivalent in neutral solutions. Any solution with pH less than 7 is acidic, and greater than 7 is basic. In acidic solutions, the concentration of hydronium is greater than that of hydroxide. In basic solutions, the concentration of hydroxide is greater than that of hydronium. The mathematical definition of pH is the following. pH is equal to the negative log of hydronium concentration. Because this is not a chemistry class, we will not go into details regarding the calculation of pH. I'm going to mention a high yield point now. In general, a 1 unit decrease in pH results in a 10 times increase in hydronium concentration. For instance, a solution with pH of 2 has 10 times more hydronium ions than a solution with pH of 3. Another example is a solution with pH of 2 has 100 times more hydronium ions than a solution with pH of 4. Some common liquids and their pH include the following. Lemon juice has a pH of 2, blood has a pH of 7.4, and bleach has a pH of 12.6. Now let's discuss how the addition of an acid or base affects pH. An acid donates a proton to increase the hydronium concentration. This decreases the pH. An example is hydrochloric acid, which donates its proton to water to form hydronium and a chloride ion. A base, on the other hand, accepts a proton to increase the hydroxide concentration. This increases the pH. An example of a base is ammonia, NH3, which extracts a proton from water to form ammonium, NH4+, and hydroxide. In living organisms, the pH of internal fluids must be maintained within a small range of values. For instance, human blood has pH of 7.4 and must be held between 7.0 and 7.8. A pH less than 7.0 or greater than 7.8 is inconsistent with life. To maintain the pH within the small range of values, buffers are needed. The main purpose of a buffer is to resist change in pH when an acid or base is added. A buffer consists of an acid and its associated base. We will present you with an example here. Let's talk about carbonic acid bicarbonate buffer using a chemical equation. Carbonic acid transfers a proton to water to form bicarbonate and hydronium. The bicarbonate is a base. A solution containing both carbonic acid and bicarbonate is a buffer. We will now focus on the hydronium concentration since it determines the pH of a solution. If there is a decrease in hydronium due to addition of base, the pH increases. The equation shifts to the right to replenish hydronium. This results in a decrease in pH. If there is an increase in hydronium due to addition of acid, the pH decreases. The equation shifts to the left to consume hydronium. This results in an increase in pH. Both of these situations demonstrate how buffers minimize pH change.